Very good morning. We are from Team Planova. So we will present our slide. So this is our executive summary. So our project title is Intelligent Waste Collection and Monitoring System. So our client will be Dewan Bandaraya Kuching Utara, which is DBKU. So the vision for our project is digital modernization of waste management through IoT and data analytics. The key innovation is IoT sensor, which are real-time monitoring of waste bin fill levels, smart routing, automated generation of optimized collection routes. The strategic impact include efficiency, minimizes operational waste and reduce fuel consumption, and environment, enhance urban cleanliness and reduces carbon footprint. So our project policy alignment will support the Sarawak Sustainability Blueprint 2030 and meets Malaysia's national environmental and smart city targets.
In recent years, many local councils in Malaysia, including DBKU, still rely on fixed waste collection routes. This often leads to inefficiencies such as unnecessary fuel usage and overflowing bins in certain areas. To address this issue, our project proposes an intelligent waste collection and monitoring system using IoT technology. The system enables real-time monitoring of bin fill levels, optimized truck routes, and data-driven decision-making. This supports cleaner city management and aligns with the Sarawak Sustainability Blueprint 2030. This project is developed by Team Planova, where each member contributes based on their expertise in project management, IoT system, data analytics, and UI/UX designs.
Moving into the heart of our technical planning from assignment 2, we developed a comprehensive work breakdown structure WBS or deliverable structure chart DSC following the waterfall technique. We chose this linear approach because our requirements for DBKU were well defined, allowing for precise scheduling and resource allocation. So our DSC is divided into 8 manageable phases, starting with initiation and moving through system analysis, design and development, right through to testing, deployment and closure. By following this structure, we ensured that every element from requirements gathering to SRS preparation was accounted for. This systematic planning served as our primary communication tool with stakeholders and was the foundation that allowed us to successfully track our milestone.
So this is our project closure and MOV framework. So this is our project closure checklist, which consists of achievement of project objective, MOV evaluation completed, system testing, stakeholder acceptance, documentation, user training, budget, lesson, project, and formal project sign off. So for our MOV evaluation, the evaluating measurable organizational value through operational data analysis and sensor log. So for our fuel consumption, we can reduce 20% of fuel consumption and reduce 50% of operational costs and 80% of bin overflowing incident. Other than that, we also can increase route efficiency and service quality.
Over a 6-month period, our learning cycle started with understanding DBKU's waste management challenges, followed by system design and development, and finally testing and evaluation. This structured approach ensures the system is practical, efficient, and ready for real-world use. These slides explain use case diagram for the intelligent waste collection and monitoring system. The diagram shows how different actors interact with the system to support efficient waste management. There are 4 main actors. The IoT sensor module sends bin fill level data to the system. The DBKU administrator manages system operation such as monitoring dashboard, updating bin information, receiving alerts, and managing users. The driver views optimized collection routes and receive overflow alerts during daily operations. The waste collection supervisor oversees operations by monitoring dashboard, checking alerts, and generating routes. The key system functions include monitoring bin levels, viewing real-time dashboards, and generating optimized routes, receiving alerts, managing data, and downloading reports. This slide summarizes our work breakdown structure, which spans from November 2025 to April 2026 and is divided into 8 phases. Each phase has clear milestones, tasks, and assigned roles, ensuring the project is well managed, structured, and completed on time. For our project, we selected a phase conversion strategy. This means the system will be implemented gradually by zones, starting with a pilot area. We chose this strategy because it minimizes operational risk, allows early detection of issues, and helps staff adapt to the new system without disrupting daily waste collection. We did not select direct cutover because it carries high risk, as any system failure could immediately disrupt operations. We also did not choose parallel conversion because running two systems at the same time will increase cost and staff workload, which does not suit the project budget constraint. In conclusion, phase conversion is the safest and most practical approach for the BKU.
Next, I will explain the cost of resources for this project. The cost estimate was carried out based on the work breakdown structure developed in part 2. Now, we have 4 categories, which is human resources, technology, facility, training, logistics, and support. It total up the project cost to 47,710 ringgit. Here is some breakdown of the cost. For human resources cost rate per hour, and we break down it by phases. And now I will tell you guys about the task linking and schedule optimization. The purpose is to analyze task dependency in the work breakdown structure and to optimize project duration using parallel activity, and also to reduce the idle time without breaking logical dependency. The dependency type applied is finish to start, starts to start, and finish to finish. Each phases use this dependency. After using the task linking, the dependency type, we get this project schedule. Now I will show you guys the critical path analysis. The critical path flow that show in the yellow, it starts from project charter to the final document, and it adds up to 100 days. Critical path tasks require strict monitoring and ensure completing within the optimal 141 days timeline. Now I'll explain about the resource allocation and leveling strategy. The leveling strategy that we apply is use of float. Delay non-critical tasks within the available float, and critical path tasks remain unchanged. And we also task rescheduling, shift documentation, and review tasks to lower load period. And secondary measure, if in fashion, we delegate the non-critical work to substitute the resources and split large tasks into smaller work package. Now, our client has decided that the project schedule needs to be cut by 10%, meanwhile the project budget must be reduced by 20%. Here, the original schedule and the revised schedule side by side. We managed to complete the client request by 10% cut for project schedule, and we managed to save 14 days. Original budget and the revised budget that fit the client needs. And we managed to save the 9,542, 20% reduction that client wants by reducing some of the human resources, technology, facility, and training support.
So this list our list of project resources. So firstly, we have our human resources, which is our team that consists of Siti Noorafiqah, which are project manager and documentation lead, Aina Amira, IoT system and sensor integration, myself Faiq, which is data analytics and route optimization, and finally we have Nurfitrisha, which are UI and UX and front end development. So for our technology and equipment, we are using a hardware which are IoT ultrasonic sensor and GPS module for real-time tracking. For software, we are using a cloud hosting, which is AWS or Firebase, utilized free or developer tier. For the system, we are using a central monitoring dashboard and route optimization algorithm. For budget and financial, our final budget is 38,168 ringgit, which is reduced by 20% from initial 47,710 ringgit. So our strategy, we are using a scope thinning and utilizing technical free tiers to optimize cost. Our support and facilities, we are using a staff training and user manual for DBKU personnel. And our data resources are DBKU field records, financial reports, and IoT system log for evaluation.
Our team plan over is modernizing DBKU's waste management to eliminate fuel waste and overflows. Aligned with the Sarawak 2030 blueprint, our IoT system targets a 20% fuel reduction, a 15% cost saving, and 80% decrease in bin overflows. Within a 200k budget, we are delivering a real-time dashboard and optimized routing for a cleaner, smarter North Kuching. Let's look at the core of our project, which is the MOV, or Measurable Organizational Value. We have identified 4 impact areas: operational efficiency, sustainability, service quality, and also transparency. Within our 6-month pilot, success is defined by 3 hard targets: a 20% reduction in fuel consumption, a 15% cut in total operational costs, and 80% decrease in bin overflow incidents. So by hitting these metrics, we don't just improve waste collection, but we also provide the BKU with a data-driven foundation for a smarter, cleaner North Kuching. To identify the best approach for the BKU, we evaluated 3 alternatives: maintaining the status quo, purchasing a software package, or building a custom system. While doing nothing is free, it fails to address fuel wastage. Purchasing an off-the-shelf package offers speed but lacks the specific customization the BKU requires. We recommend a custom-built system because it ensures data security, supports local innovation, and provides the scalability needed to meet the Sarawak Sustainability Blueprint 2030 goals. It is the only option that delivers the highest long-term value for North Kuching. To protect the BKU's investment against our 20% budget cut and 10% time reduction, we have integrated a 5-phase risk strategy. In initialization, we face inaccurate MOV. We are mitigating this by focusing on high-density zone to maintain high impact with fewer resources. In planning, we face schedule compression. We are using avoidance by fast-tracking sensor procurement to overlap with our design phase, eliminating any wait time. During execution, we address hardware failure from Sarawak's weather. We have chosen acceptance but built local data lock-in into our code to prevent data loss during outages. At closing, to handle user resistance, we are mitigating this with a driver-first UI and hands-on workshop to ensure adoption. Finally, for evaluation, we use transference, handling our analytical tools to the BKU's IT team to verify our 15% cost-saving target long-term. This strategy ensures our system remains robust and high value.
So for conclusion, there are 5 things which are measurable value, MOV. The system is designed to achieve a 20% reduction in fuel consumption, a 15% cut in operational costs, and an 80% drop in bin overflow. For schedule optimization, the task overlapping reduce the project duration from 181 days to 127 days. For our budget efficiency, we achieve a 20% cost saving and bringing the total final budget to 38,168 ringgit. For our service quality, we improve our real-time reporting leads to higher public certification and better resource management for the council. For final outlook, the project provides a scalable, high ROI framework ready for full-scale municipal adoption across North Kuching.